phase network and the single phase transformer, right? So we are going to do the experiment on DC generator today. So as we have discussed in the lecture class, that we have different type of DC generators, right? Can you remember? So and the types of the DC generators depend upon how the armature and the field circuits are connected with each other. So if they are not connected at all, we call them separately excited DC generator. Yes. So the number one is separately excited DC generator. Okay. And then if we connect the armature circuit with the field circuit, we call them self-excited DC generator. Now based on how you connect them, there are different types. If the field winding and the armature winding are connected in series, we call them series self-excited DC generator. If they are connected in parallel, we call it shunt. And if there is a series and shunt both branch, we call them compound. So actually in our today's experiment, we will use all of them. Okay? In the manual, you will see like there are different steps. Step 1 using separately excited, then self-excited, this, that, and so on. So ideally they are not very different from each other. They are very similar. Why? Because you just need to change 1 2 wire. One wire or 2 wires to make it from series to shunt. You understand? Before they were in series, you connect it parallel. That's it. And from series and shunt, you just make it compound. It's very easy. Okay? But now, what is our target actually in today's experiment? What is our objective? For example, this is the main thing to understand. Every experiment, there are some targets. For example, when we did the experiment with transformer, what was our target? To find the efficiency, to find the voltage regulation, to find the equivalent circuit parameters, right? RC, XM, R equivalent, X equivalent, and that to get that, we did different type of tests, right? Open circuit test, short circuit test, and so on. So, but our main focus is on the objectives. Similarly, the experiment today is DC generator characteristics. Characteristics means behavior. And what are the behavior or the characteristics of a DC machine or DC generator? We started in the lecture class. One of them is open circuit characteristics. Can you remember open circuit characteristics? Open circuit characteristics is actually, if you can remember, in the generator side, okay, in the generator, we have a field circuit. This is LF, inductor of the field, and we apply a particular voltage, which is VF. Because of that, this IF flows, right? And whenever there is a field, this armature starts rotating, right? This is what? Armature, right? And inside this armature, we generate like the voltage gets generated, EA, and it starts, it starts giving the output. We connect our load over here, right? Now in the open circuit test or open circuit characteristics, what we do? We don't connect anything here. No load. Open circuit. And this, like you can see it from the name, it is open circuit, right? So that means your load side will be open. But what we do, we put a voltmeter here. Voltmeter. So that we can measure the open circuit voltage, which is EOC, open circuit. Okay? And then what we do, we try to plot this voltage open circuit with respect to field current. With respect to what? Field current. Now, in this chapter, understanding these different type of curves is very important. Very, very important. Okay? Like if I ask, what is the open circuit character? What is the OCC curve for a DC generator? Within a second, you need to understand what I am talking about. I am talking about the curve, which is voltage versus field current. You understand? So OCC curve is what? Voltage open circuit versus field current. Are you with me? Like this voltage open circuit is not in the field. This is in the armature. And this field circuit, field current is not in the armature. This is in the field. So they are in two different circuits. But actually the relationship is that if you increase the field current, what happens? The field is getting stronger, and because of that armature is getting more electrical energy, right? So that means we get the curve something like this. More we increase the field, EA is getting increased, and then it reaches to the saturation. Are you with me?
Yes.
This is same like the magnetization curve we plotted in chapter number 2. B versus H characteristics curve. Remember magnetization curve? This is looking similar, right? Now, we usually don't start from 0 volt. Have you noticed? I have started just above the 0. Can you remember why?
But doctor, this is only for the self-excited.
Not self, this is separately excited.
No, this is.
Oh,
no.
this one. Yes. No, like this residual magnetism is present everywhere.
Ah,
But in self-excited, we take the advantage of this.
okay.
You understand?
Yeah.
Because the residual magnetism is everywhere, but in separately excited, we don't need it because we have a separate excitation. But in self-excited, we take this advantage of this, stored residual magnetism. Like we discussed this in lecture. If you have question, we can discuss again in the lecture class. Okay, I don't want to go over there. So this is our OCC curve. OCC curve. What does it mean? Open circuit characteristics curve. So this is our first work. Okay, first work is to find the open circuit characteristics curve. Okay, tell me, which type of generator we prefer or always we use to find the open circuit characteristics? Which type of generator? We use separately excited. Why? Because only in the separately excited generator we can control field current. Are you with me?
Yes.
You see, like this in x-axis we have IF, right? So to get a good plot, so we need to have a control on IF, right? So in the separately excited DC generator, we have a separate voltage source for field. So we increase slowly, and we press F9, and we get the curve. You understand?
Yes.
But for series or shunt or compound, what happens? It generates automatically, and you cannot get a good curve for OCC. Are you with me?
Yeah.
You understand this point?
Yeah.
So this can be a question even in the lab final or anywhere, like why we choose or what type of generator we choose to get OCC curve and why. Always we choose separately excited DC generator. Why? Because in separately excited DC generator we have control over field current, and in open circuit characteristics curve we need to change the field current, and thus we get. Is it clear? Okay. So this is the first step. Okay, this is the first step, like the first target to get the OCC curve. The next one is load characteristics. So from the name you can understand, like this is the behavior of the load. So what we do, So what we do, we instead of keeping it open, we make it connected with a load. Okay, what type of load? Resistive load actually. Okay, so I will show you the picture. Like in this type of experiments, understanding the picture is very important. Okay, so this load is connected, and like this EA is here. Okay, and this is our field circuit. So now can you tell me what type of generator is this for the load characteristics? For the load characteristics, this picture is for separately excited, right? Because still there is a separate excitation over here, isn't it?
Yes.
Are you with me?
Yes.
So because this is separately excited, so what we'll do, we'll apply some field and turn on the motor so that the armature rotates, and then it generates the electrical energy. So what we will plot? We will plot the load characteristics, and load characteristics is VL versus IL. You understand? What is the BL like? If you change the resistor, what is the behavior of the voltage and the current in the load side? Clear? You understand? So this one we will do for all of them. We will do for separately excited, we will do for series self-excited, we will do for shunt self-excited, and we will do for compound self-excited. You understand? And for each of them, all of them, we will plot VL versus IL curve, at the same plot. For example, this is for separately excited, this is for series, this is for shunt, So what we will do? We will change the connection, but we will plot in the same plane. Why? So that we can compare between each other. You understand? I think some of you asked me in the previous class, in the lecture, that doctor, we have different types. What is the advantage of this type or this type or this type? Like how we understand that which one we need? It depends upon, like what type of load characteristics you are getting. You understand what I'm saying? For example, for a particular generator, the load characteristics you are getting, this one, it is matching with what your load demands. What is your requirement? So that's why we take this one and so on. So that's why what we do, we will do the load characteristics for all of them and we'll plot them together in the same curve. Okay? So this is what we'll do. Now, let me elaborate a little bit. Is that how to do the experiment with separately excited DC generator? This is clear to us, right?
Yeah.
Like this is a separate excitation. This is separate excitation, right? And this is our armature. This is field circuit. This is armature circuit, right? So we will apply the field and then we will calculate the value of voltage and current. We will plot the curve, right? Now, if we want to make self-excited series, what we have to do? Make it series with whom to whom?
With the load.
With the load?
No, with the armature.
With the armature. Will it be present?
What?
This will be present or no?
Yes.
This will be present? No. You see, this is you have to understand. In the self-excited, there is no separate field. The field winding is where? The field winding is here. You understand? And using the advantage of this residual magnetism, it will generate the output voltage automatically. You understand? So whenever we'll do the series, we will connect the field winding here in series. When it is shunt, we connect it in shunt. This is shunt. When this is compound, there will be one more here. This is compound. Is it clear?
Yes.
Are you with me? Is it clear?
Yes.
So this is how actually we will change the connection and we will cover all the different type of generators. Okay? We'll start with separately excited DC generator. Just I'm summing up. Guys, everyone, I'm just giving you a very quick summary of what we are going to do. This thing you need to understand, because in this experiment there are different steps. You understand? This type of labs, if you just read the manual and do the experiment, it's very difficult. You'll never understand what's going on, because a step after a step after a step, there are different steps, and you'll do lots of things, but eventually, what is your main target, what is your main purpose, it will not be clear to you unless you understand what, like your teacher. You understand? So if you understand what I'm saying here, that what is our target and why we are doing what, then whenever you'll go to the table, your conception will be clear that yes, I'm doing this because of this. You understand? So just I'm giving you a summary. In this experiment, we are trying to find the characteristics of a DC generator. Two characteristics. One is open circuit characteristics, and to find that, we will use separately excited DC generator. And what is the open circuit characteristics? This is field current versus open circuit voltage. So we keep the load side open, we'll change the field, we'll see how it behaves. Clear?
Yes.
Okay. Second objective, load characteristics. So we will see that for different type of generators, how the change of the load behaves. And the load characteristics is voltage load versus current load. So what we will do? We will do it for different type of generators. So first we will do for separately excited, we will plot a curve. Then we keep the curve. Then we change the connection, make it series, self-excited. And then we plot the curve for series self-excited on the same plane. And then we repeat the same thing for shunt, we repeat the same thing for compound. And thus we'll get a curve, a series of curves, okay, where we have the behavior or the characteristics of different type of generators. So that as a customer, as an engineer, as a designer, if you need to know that which generator you need to choose, you can look at the curve picture. So our connection is ready and the Cassie lab is ready also. So we want to do the open circuit characteristics. So we have put the open circuit voltage in the y-axis and the field current in the x-axis. So for different values of field current, we will measure the value of EA, and thus we will plot the curve. And one more thing we have here is the speed. N is the number of rotation per minute. So to measure that, we have connected with a tachometer. This is the tachometer we have, and this tachometer provides us the speed. Okay. So now, first of all, we will turn on the supply for the motor. Okay, this is the supply for the motor. We will increase the voltage so that it reaches 1700 RPM. So when we increase the voltage, we have to look at the speed. It reaches 1700 RPM. So we increase it slowly. So it's very close to 1700. So now what is happening? The rotor is rotating, and it is rotating in 1700 RPM, but still there is no output from the generator. Why? Because the field is off, right? So we need to turn on the field now. So you see this E1, E2 is the field which is connected with this source. So this is the source to give the field supply. So now we will turn on the field, make sure that the voltage is 0 position, turn on the field, and now we will increase it slowly, and we will take the data in different steps. Okay, so it is in 0. So take the first reading, press F9 please. Okay, then we increase it to a little more, press F9. F9 please. F9. So in the manual it is said that we will do this work until we reach here 0.332. F9. 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 F9, F9. Okay, so we have taken some data, and now if we just plot it, it is already plotted. So we can see the curve look like this. Actually, it is not the very perfect curve, because the perfect curve should reach the saturation. But we stopped before we reach the saturation, okay, as instructed by the manual, because maybe if we increase more, it will cross the limit of the machine or something like that. So we'll not do that. Like whatever instructed over here, we just follow that one. So this is the open circuit characteristics for the DC generator, and we did that by using the separately excited DC generator. Clear? So inshallah, in the next step we will go for the load characteristics. Self-excited shunt. Okay, the armature coil is connected as a parallel to the field coil, or vice versa, whatever it is. So first step is to turn on the motor's source and increase the voltage so that you reach 1700 RPM. RPM, right? 1607. Okay, well. So we are seeing a little voltage over there, but the output is very small. The current is 0, right? Why the current is 0? Current shouldn't be 0.